Okay, then welcome everyone to the last lecture of Yann Palu, who is continuing his series on extriangulated categories.
Thank you. Let me recall from yesterday that A is a basic finite dimensional gentle algebra over an algebraically closed field K. And I will assume the gentle algebra to be of finite representation type. So we've seen that from a gentle bound quiver, it's possible to form its blossoming by adding new sinks, sources, and arrows so as to make all vertex of Q 4-valent. So here's an example. And we've defined walks on Qi as maximal strings for the blossoming bound quiver. So this was a generalization of the notion of walk in a grid by Thomas McConville. And from a result by Brüssler, Douville, Moussavant, Thomas, Yildirim, and a collaboration with Vincent Pilot and Pierre-Guy Plamondon, the combinatorics of walks, that was called non-kissing, is categorified using tau tilting theory. So it corresponds to tau rigidity at the level of representations over the gentle algebra. Okay, and I will also use a result due to Butler and Ringel. That the intercomposable representations for Qi are completely parametrized by strings over Qi. So they are given by string modules. Okay, and what we wanted to do is try and find some extriangulated category that would categorify the bending walks over Q. And here's how to try and define one. So let W be the full subcategory of mod A blossom. Whose objects are the string modules associated with the walks. So M sigma is in W if and only if sigma is a walk. So it starts at a blossom and ends in a blossom. Okay, sorry. So here's W. And it turns out that it's possible to prove that W is closed under extensions inside mod A blossom. W. And so it's an exact category. Moreover, so we wanted some exact structure on walks, so that walks that turn only once would behave like projective or injective objects. And that's what happens for this exact structure. So if M is indecomposable, mod A blossom, then it is projective in W, but not injective, if and only if it is of the form Pi, some projective A blossom module, where I is a vertex already in Q. So not one of the leaves of Q blossom. And similarly, M is injective, but not projective, if and only if it is some injective A blossom module at a vertex already in Q. So the strings for those Pi and Ij look like that. So there's a vertex I, and then one can follow the longest possible path starting from I, and there are at most 2 such paths. And that gives you the string for Pi, and the string for Ij is given by this string. So they do correspond to the walks that turn only once. Now M is both projective and injective. If and only if it is a projective module at a source, and that's equivalent to being an injective at a sink. And for those indecomposable modules, the string is just a path, so something like that, from I to J. And then W has 2 very nice properties. The first one is that every object in W has projective dimension at most 1. So there is a conflation P minus 1 of short exact sequence P minus 1 to P naught to M, where P naught and P minus 1 are projectives in W. And second nice property is that for every projective object in W, there exists a short exact sequence of the form P to Q to I, where I is injective, while Q is both projective and injective. And this short exact sequence is easy to picture using strings on, say, start with Pi, the indecomposable projective at I. It injects into the direct sum of 2 paths. Containing I. And the quotient is the injective at I. So those last 2 properties are will turn out to be quite important. And so they will deserve a name. And well, the first one says that every object is of projective dimension at most 1. So we can say that the category is of global dimension at most 1. And the second one says that in an injective resolution of projective objects, the first injective is also projective. So we'll call that dominant dimension at least 1. So in the end, we're going to call extriangulated categories with those two properties 0 Auslander. And before giving the explicit definition, I want to show that there are more examples of such. So if you look at module categories, there are very few 0 Auslander module categories. You only get the module category over AN with linear orientation. But when you step into the extriangulated world, then there are many more examples. So the category of walks is such an example. And another example arises from the work by Adachi, Iyama, Reiten, and tau tilting theory. So fix a finite dimensional K algebra lambda. And consider C to be the full extension closed subcategory of KB proj lambda formed by complexes of concentrated in only 2 degrees. So K minus 1, 0 proj lambda inside KB proj. So the objects there are the complexes concentrated in degrees minus 1 and 0. And morphisms are morphisms of complexes up to homotopy. Now there's a functor from C to mod lambda. That's obtained by taking H0. And this, well, H0 obviously kills complexes concentrated in degree minus 1, so the shifts of lambda. And so it factors through the quotients of C by sigma of lambda. And by results due to Verne, Marsh, Reiten, and later generalized by Keller, Reiten, Koenig, Jules, Iyama, Yoshino, the induced functor is an equivalence of categories. So we've seen from David's lectures that there are some specific modules of interest that are called support tau tilting. Inside mod lambda. They were introduced and studied by Adachi, Iyama, Reiten, who also showed that there's a bijection between the support tau tilting modules and silting objects in KB proj lambda that are concentrated in degrees minus 1 and 0. So these are called two-term silting objects. And both families of objects have a very nice theory of mutation. And my point today is to try and convince you that the reason that there is a nice theory of mutation here is because there are some 0 Auslander extriangulated categories involved. So the category C here enjoys very similar properties to the category W. So first, if P minus 1 D P0 is an object in C, then there exists a next triangle in C, which means a triangle in KB-Proj with 3 terms in C on the following form. P minus 1 goes to P0, both concentrated in degree 0 with map T, and then taking the mapping cone gives you the 2-term complex you started with. The complexes concentrated in degree 0 are projective objects in C. So we do get global dimension at most 1. And there's an obvious X triangle that's obtained by sending lambda to 0 and then taking the cone, which is the shift of lambda. And well, lambda concentrated in degree 0 is projective. Its shift is concentrated in degree -1, and it turns out to be injective in C. And of course, 0 is projective injective. So we're in a very similar situation as in the case of the category of walks, W. A third example is as appeared in work in collaboration with Arnaud Padrol, Vincent Pilot, and Pierre-Guy Plamondon. So here we consider a cluster category C. So in the home finite case. And we fix a cluster tilting object. Some basic cluster tilting objects. So recall that it means that it's rigid, so there are no non-zero morphisms from T to its shift, first shifts, and it's a X1 orthogonal. The X1 orthogonal of T is T itself. So if X1C T, X1 X T equals 0, or X1 Tx equals 0, then all indecomposable summands of X are isomorphic to T1, T2, or Tn. So in that setting, it was proven by Brand, Marsh, and Rayton that every object in C admits a specific triangle. So there exists a triangle of the following form. Sum of Ti Bi to sum of Ti Ai to X. These triangles are useful to define indices in cluster categories. So indices were studied by Dehi and Keller, and they also appeared in my PhD thesis. And the index of X with respect to T is the vector AI minus BI obtained from such a triangle. Indices are interesting in that they categorify G vectors of cluster algebras. So they should be thought of as a categorical version of G vectors. Okay. a lemma on indices says that given a triangle x, y, z, sigma x, where the morphism from z to sigma x factors through add sigma t. So where there exists a factorization through some sigma tk, then the index of y is the sum of the index of x and the index of z. Yes, so indices behave very well with respect to those specific triangles, but they are usually not additive on triangles. So this means that if one wants to study G vectors, it's interesting to only consider those triangles and forget about all the others. And so if you endo C with only those triangles, you would get something that's well adapted to studying G vectors. And from the result by Hiroyuki Nakaoka that I mentioned on Tuesday on relative extriangulated structures, looking at those triangles only would give an extriangulated substructure of the triangulated structure of C. So this is extriangulated. And I will write E sub t for the corresponding bifunctor of the extriangulated structure. And remark that once more, for this extriangulated structure, C satisfies some nice properties. So first, remark that T has now become projective. And this can be seen easily if consider any morphism from T to the codomain of a deflation. Then composing with the cone, that would be a morphism from T to sigma x that factors through sigma t. But T being rigid, there's only the zero morphism from C to sigma t, so this has to vanish. And therefore there's a lift here, which means that T lifts against every deflation, so it's projective. Moreover, any object is in C has projective dimension at most 1, and that comes from the triangles of Brand, Marsh, and Rayton. So there is t-1 to t0 to x. So that's a triangle where the connecting morphism goes from x to sigma t-1, so it obviously factors through at sigma t. And so that's an X triangle. And finally, there is a conflation t to 0 to sigma t that comes from the triangle given by the identity. And the identity of sigma t does factor through at sigma t. So this is an X triangle. Again, we have seen that P is projective, but one can similarly check that sigma t is injective for this extriangulated structure. So we are again in the case of say dominant dimension at least one. Okay, so that gives three, at least seemingly quite different examples where those two properties arise. And we are going to study mutations in that setting. So that's work in progress with Miszagorski, Hiroyuki Nakaoka. So an extriangulated category C is called zero Auslander. If it satisfies those two properties that appeared in the previous examples. So if every object X in C has projective dimension at most one, so if there exists an X triangle P minus one P naught X with projectives, and if for every projective object in C there exists an X triangle P to Q to I, where I is injective and Q is both projective and injective. So as I quickly said earlier, the category of modules over AN with linear orientation is zero Auslander. But it's the only module category that is zero Auslander. Now the examples we've looked at before, so K minus 1, 0, proj lambda is zero Auslander. And it's even reduced zero Auslander. So reduced means that there are the only projective injective object is the zero object. So if instead of looking at morphisms of complexes up to homotopy, one would look at morphisms of complexes, the category of two-term complexes of projectives, not up to homotopy. One gets again a zero Auslander extriangulated category, but that one is non-reduced. So there are some projective injective objects there that correspond to complexes of the form P identity P. Now, as we have just seen, cluster categories with a relative extriangulated structure making T projective is reduced zero Auslander. The category of walks, W, so it's an exact zero Auslander category. But from the combinatorial point of view, straight walks are irrelevant and they correspond to projective injective objects in W. So we can look at the quotients by projective injectives. And this one is extriangulated and reduced zero Auslander. Yes, and there are more examples. Let's say, for example, extended cohorts of Coty structures. in triangulated categories. Those are reduced zero Auslander. A quick remark. It's possible to define indices in any zero Auslander extriangulated category. So one can talk about G vectors. And it's also possible to define a categorical version of C vectors. And that's following Jorgensen and Yakimov. Okay. So we now fix a zero Auslander extriangulated category C. And for simplicity, I will assume that it is Kohlschmidt reduced and that the projective objects are of the form ads of P, where P is some fixed basic projective. So from those assumptions, it follows that there is an extriangle of the form P to 0 to I, with I injective. And it turns out that I is an additive generator of the subcategory of injective objects. Now we are going to consider some maximal rigid objects in C. So we'll let R be a rigid object. So this means that E of R equals 0. So any X triangle with both end terms R splits. And now there are many possible notions of maximality that arise in the literature. So the obvious one is maximal rigid. So if R is rigid and maximal with that for that property, so meaning that if R plus X is rigid, then we haven't added any new cement, so X is in add R. But there are other possible choices. We could look at a tilting version of maximality. So R would be called tilting if there exists an X triangle starting at P, or the projective generator, and with two terms in add of R. Similarly, one could look at the co-tilting condition, so saying that there exists an X triangle R0 R1 to R0 to I, where I is the objects that appeared here. And two more definitions, and that will be it. It's called E-tilting. If the only object that's X orthogonal both to the left and to the right of R is R itself. So E X R equals 0 equals ERX implies X is in add R. So note that it is a weaker condition than cluster tilting. Cluster tilting says that any one of those two equalities implies the conclusion. Here we require both vanishings. And R is said to be complete rigid if the number of isomorphism classes of summands of indecomposable summands of R is the same as that for P. So the name complete rigid is justified by the following property. So if R is rigid, then its number of summands, or pairwise non-isomorphic summands, is bounded by n. So complete rigid have the maximum possible number of summands. And second point, which might not come as a surprise, but its definitions A to E are all equivalent. Okay. So in fact, for proving that A, B, C, and D are equivalent, there is no need to assume Kohlschmidt and no need to assume that projectives are given by an additive generator. Now, finally, I said in the first lecture that I would present some new results. So that's finally some results appear. So that's in the collaboration with Misha Gorsky and Hiroyuki Nakaoka. So will let C be reduced zero Auslander? And that we also assume Kohlschmidt. And again, we write proj C, we assume that it's given by add P. And now we consider some tilting objects there. So that R equals R bar plus X. Assume that it's a basic tilting object in C, where X is indecomposable. Then there is a unique isomorphism class of indecomposable objects Y that are not isomorphic to X, but such that R bar plus Y is again tilting. So this means that there is a mutation for tilting objects in zero Auslander extriangulated categories. Yes, and we can say a bit more. there is precisely one exchange X triangle relating X and Y. And it's either of the form X to E to Y with E in add of our bar, or Y to E prime to X. Okay, so this looks more like tau tilting theory or silting theory than cluster tilting theory in two Calabi-Yau triangulated categories. In cluster categories, there are two exchange triangles, one on each side. However, on those two exchange triangles in a cluster category, only one of them has a connecting morphism that factors through at sigma t. And that's the one we see in this theorem. So if we apply the results to the examples we've seen above, we recover several known mutation theories. So we recover two-term silting mutation. So that's by applying the theorem to k minus 10 of proj lambda. And via a Adachiyama items bijection, we thus recover tau tilting mutation. So we recover cluster tilting. By applying the theorem to cluster categories with their relative extriangulated structures. So one of the two triangles is missing for cluster tilting theory, but because the category is two Calabi-Yau, we know that the second one will exist also. If we apply to the category of walks, we recover flips of non-kissing facets. So I'm going to apply to W. And we recover also mutation of relative tilting objects. In the sense of Yang and Jules. Where, so if lambda is a cluster tilted algebra, support tau tilting theory over lambda is the image of cluster tilting theory on the cluster category. Now, relative tilting is answering the question, if you take the endomorphism algebra of a cluster tilting object in, a cluster tilting object in a triangulated category, which is not necessarily two Calabi-Yau, then you can look at the endomorphism algebra of such a cluster tilting object, and there is a tau tilting theory for this algebra. And the natural question is, which objects in the triangulated category correspond to support tau tilting modules with the endomorphism algebra? And those are the relative tilting objects. And in this case, our result is not new. So there are already results on mutations for relative tilting objects. However, the proofs given in the literature always involve tau tilting theory at some point. So our result is giving a new proof of relative tilting mutation without appealing to support tau tilting theory. And yes, this will end my series of lectures. thank you for your attention.
Thank you very much for this very nice lecture. Are there any questions? There's a question in the chat from Aaron Chan. Whether S0 Auslander extriangulated categories always have Auslander writing theory?
Okay, so that's a good question. I don't think it's necessary in full generality, but it works in all the examples I've given. So there's always AR theory there. Yes, that's definitely something to investigate. So maybe in the X finite case, there is a chance that it's always true. I would have to think more about it.
Other questions? Yes, Dave.
So can we by any chance see your last slide again?
Oh yes, sorry.
And so in the statement of this last theorem, you've essentially got a way to define irreducible mutation. Can you extend that to arbitrary mutation? Replacing any number of somehow.
Yes, yes. So our proof does not work if X is not indecomposable. So our strategy is a bit similar to Yamayoshino's strategy. So we use reduction to reduce to the case where our basic tilting object is indecomposable. And there we show that the only possibility for this indecomposable basic tilting object is either that it's projective or injective. Yes, so reduction might help saying things about more segments, but there needs to be more work done if you want to work with more segments.
Can I ask about the generalization in another direction? So the setting seems to be sort of projective dimension 1 for these examples.
Yes.
What about saying if I take n-term complexes, can anything be said? Or
so yes. So n-term complexes would be n-2 Auslander. And in that setting, we have proven the equivalence of so you might guess possible generalizations of the definitions of tilting, co-tilting, e-tilting in that setting. And they're again all equivalent. Yes, but we do not have any results on mutation in that setting yet. So we are strongly suspecting that there are n possible replacements or complements for an almost complete tilting object, but yes, we haven't had time to look at that case yet.
thank you.
Okay, well then in the interest of time, I would say let's thank Yann for his series again.